Imagine a technology, something so revolutionary, it's literally reshaping our world right now. Yet, maybe just a few decades back, it was largely dismissed, even kind of ridiculed in some circles.
Right.
We're talking about the very heart of modern AI neural networks. It's easy now to look at all the breakthroughs,
Yeah.
self-driving cars, amazing image generation, and think, okay, this was always going to happen, like a straight line upwards.
Yeah, it feels inevitable in hindsight, doesn't it?
Exactly. But the real story is much more dramatic. For years, these brain-inspired systems, they were sidelined, considered like academic curiosities, only really good for solving what researchers themselves called,
Yeah.
and maybe with a bit of shade, toy problems.
Toy problems. Yeah, it sounds almost dismissive now, but it reflected the reality then.
Okay, let's unpack this then. Today we're going on a pretty fascinating journey, I think, through the history of neural networks. We're tracing their, well, improbable path from being these academic playthings to becoming the powerhouse engines driving today's AI. Our mission really is to get why they struggled so much with real-world data. Before we had big data and the kind of computing power we see now with GPUs,
Right, what were those specific roadblocks?
we'll dig into the big ones. Overfitting was huge. The fundamental lack of scale in the early systems and just the raw computational limits they were up against seemed impossible for decades.
Yeah.
But maybe more importantly, you'll see how just the sheer persistence of researchers through those lean years, let's call them, was absolutely critical. It meant that when the data and the hardware finally showed up, neural nets weren't starting from zero. They were actually ready to explode onto the scene.
Poised for that moment.
Yeah. So we'll kick off with the infamous perceptron pessimism that really cast a shadow back in the late 60s. Then we'll dissect the really deep technical hurdles. And finally, we'll celebrate the quiet, determined work that laid all the groundwork for the AI revolution we're living through.
And it's compelling, isn't it? How the core problems they were wrestling with back then, scale, data quality, quantity, the compute ceiling, they still echo today, just in different forms, maybe more complex forms, even with our advanced AI.
That's a great point.
It really makes you wonder, doesn't it? What does it even mean for a problem in AI to be truly solved? Because it feels like the goalposts just keep moving. Or maybe we're just finding new ways these old challenges pop up again.
Okay, so for many people, the story of neural networks really took a nosedive, maybe even devastating one, with this book in 1969, Perceptrons, by Marvin Minsky and Seymour Papert.
A landmark book, yeah, but not necessarily in a good way for neural nets at the time.
Right. It wasn't just, another paper critiquing things. It was seen by many as the definitive statement on the fundamental, built-in limits of these early network machines.
It really landed heavily.
Totally. It cast this long, cold shadow over the whole field, prompted a big shift in AI research that lasted for years. And the core criticism Minsky and Papert had was, well, it was incredibly stark. They basically argued that these early networks had no way to represent the knowledge required for solving certain problems.
That's the crucial bit, isn't it? The representation of knowledge.
Exactly. It wasn't just a small technical detail. It hit right at the heart of what it means for a machine to understand or learn anything complex. They famously suggested, and this quote really echoed for decades, that no machine can learn to recognize X unless it possesses at least potentially some scheme for representing X.
Right, so you can't just throw raw pixels at it and expect it to figure out cat without some internal way to build up features like edges or shapes or connectedness even.
Precisely. They were saying, look, without some way, either pre-programmed or learned internally, to grasp the features of an X, its lines, its angles, maybe how its parts connect, a simple perceptron couldn't really learn to recognize it reliably. It was a major blow, mathematically and philosophically, to that simple brain-inspired input-output learning idea.
And the impact.
Immediate and profound. It led straight into this period where connectionism was in the relative eclipse. Connectionism, being the term for neural network research back then, focusing on those connections. Funding dried up, researchers shifted focus.
The first AI winter, essentially, for that branch.
You could say that. Minsky and Papert themselves, looking back later, kind of framed it as a necessary interlude. They said, to make further progress, connectionists would have to take time off and develop adequate ideas about the representation of knowledge.
Which implies the basic learning mechanism wasn't enough. You needed better internal structure, better ways to represent what was being learned.
Exactly. Without understanding how knowledge is structured inside the system, just tweaking connection weights, like those early perceptrons did, was fundamentally limited for anything complex.
That's a critical point. And it really underlines that this wasn't just about the specific limits of single-layer perceptrons, which, let's be honest, were pretty limited. They couldn't even solve things like the basic XOR logic problem.
Right, the classic example.
But the book highlighted something deeper, a challenge for any machine learning system back then. How do you represent and learn complex patterns if you don't have the internal structure or, frankly, the computational horsepower to find them?
Yeah.
The book's big message, the one that stuck, was that doing well on small toy problems, these simplified controlled setups, it just didn't automatically mean you could handle larger problems of the same kind. That jump from the lab toy to the messy real world was massive.
And they showed it quite concretely, didn't they, with that connectedness example?
They did. They spent months, apparently, formally proving that perceptrons were unable to do something that seems really basic to us now.
Yeah.
Recognizing connectedness in a visual pattern. Like, is there a continuous line across this image?
Yeah, seems simple.
But for those architectures, it was a huge puzzle. It starkly showed the limits weren't just about needing more data or faster computers. The architecture itself lacked the capacity to build and manipulate abstract concepts like connectedness. It couldn't represent it internally.
And, it wasn't only neural networks hitting these scaling walls. This was a broader issue across early AI.
Oh, definitely.
Even the approaches based on symbolic logic or the more traditional search algorithms, they just slammed into computational limits when they tried to tackle anything approaching real-world complexity. It was a bottleneck for the whole field, really. Ambition was way ahead of the tech.
Absolutely.
Hey, like basic search algorithms, breadth-first search, for instance.
Sure.
Okay, theoretically sound, it'll find an answer if one exists, eventually. But its time and space needs, not so good, as the source puts it mildly.
Exponential growth, right? That OBD.
Exactly. B is the branching factor, how many choices you have at each step, and D is the depth, how many steps you need. So if you're searching a uniform tree where every state has B successors, maybe 10 choices at each step, and you need to look 50 steps deep.
Forget it. 10 to the power of 50, it's astronomical.
Completely infeasible for anything non-trivial. Then you had things like constraint satisfaction problems, CSPs. Early systems like Prolog could handle finite domain CSPs. Okay. Think Sudoku. Each square has a limited set of possibilities, 1 to 9.
Right, discrete and bounded.
But trying to move to infinite domain CSPs, like problems with integer or real-valued variables, that needed quite different algorithms and was way harder.
Because the possibilities become endless, continuous, like real-world measurements.
Precisely. It shows that huge leap from neat, constrained toy problems to the continuous, unbounded nature of real data. Even classical planning, with logical agents using domain-independent heuristics, general rules of thumb, they struggled too. They often used ground variable-free propositional inference, meaning they had to map out every single possible state in action.
Which just explodes combinatorially.
Yeah, they'd get swamped when there were many actions and states. A simple action like moving a step forward in, say, the Wumpus World game. You might need to repeat that logic for all 4 agent orientations, t-time steps, and end locations. The number of states just balloons.
It becomes intractable very quickly.
And even early language models, simple statistical models, n-grams, sequences of words. Early versions apparently only used unigram frequencies, just single word counts. Why? Because even big-gram frequency tables were too large to store on the device. Just storing pairs of words was too much.
Wow, that really drives home the hardware limitation. Just basic storage is a bottleneck.
It's a perfect example, isn't it? How the sheer lack of scale and computing power directly choked off even simple AI applications.
It is. And it's compelling to see how, when the compute just isn't there, even brilliant theoretical ideas are stuck. The weather prediction story is such a perfect analogy for this exact thing.
Right. You mentioned that earlier.
Yeah, early 20th century, the math, the basic equations to simulate weather, they were mostly understood. The theory was there. But it took until the 1940s for the computational power to actually run those simulations.
Decades later.
Decades! You needed people like John von Neumann driving the creation of those early powerful computers, like the one at Princeton. That machine could finally take those equations and crunch the numbers to make predictions.
But even then, it wasn't instant public forecast.
No way! It was the mid-1950s, really, before regular weather forecasts became a thing in North America. The ideas were solid, way ahead of their time, but the hardware had to catch up before they could become practical. That gap between theory and capability, that was the story for so much of early AI, including neural nets.
Okay, so with those kind of background limits, set both for NNs and AI generally, Let's zero in on the really specific challenges that made neural networks seem stuck on those toy problems. One of the biggest, slipperiest problems, especially with limited, often messy data, was overfitting.
Yes, overfitting, the bane of machine learning.
Totally. You can picture, right? Trying to draw a really complicated, wiggly line that hits every single one of just a few scattered data points.
Yeah, you nail the training data perfectly.
Perfectly. But then a new point comes along, one it hasn't seen. Your super wiggly line completely misses it, makes a crazy prediction. Because it didn't learn the general trend, it just memorized the noise and the specifics of the training examples. No real generalization.
Riddle.
Very brittle. And this was made worse by the math involved. For simpler models, like basic linear regression, the error function, how far off your predictions are, is usually a quadratic function of the weights. Nice, smooth, bowl shape, easy to find the bottom, the best solution. There's often an exact enclosed form solution, a formula you can just use.
Mathematically convenient.
Right. But for neural networks, the nonlinearity, all of those complex interactions between layers, makes most interesting loss functions non-convex.
The rugged mountain range analogy.
Yeah.
Lots of peaks and valleys.
Exactly. Finding the absolute lowest point in that landscape is tough. Standard optimization methods like stochastic gradient descent, SGD. Well, they struggled. SGD is like, taking small steps downhill from where you are. But on these non-convex surfaces, SGD has no such convergence guarantee to the global minimum.
It can get stuck.
Easily. It's sensitive to the values of the initial parameters. Where you start your descent matters a lot. You could easily end up in a local optimum, a little dip that looks like the bottom nearby. But isn't the true global optimum the best overall solution for the whole problem?
And there could be loads of those local minima.
Loads. Many local optimum that are not a global optimum. So the network might just settle for good enough, unable to find the truly best answer. And then add in real-world data noise. Most data sets have some number of mistakes in the style labels. The correct answer in the training data might actually be wrong.
Right, so trying too hard to fit those mistakes is actually harmful.
Exactly. It can be harmful to maximize log PYX when Y is a mistake. With limited, noisy data, the network would just diligently learn those errors, treating noise like a real pattern, making it useless on new, clean data.
It's compelling, isn't it, that overfitting isn't just some historical problem. It's still a constant battle.
True.
But the key difference back then was the lack of massive data sets. Without that volume, the networks they memorized the examples they saw, flaws and all, noise, errors, everything. They couldn't generalize.
So they were incredibly fragile.
Totally fragile, useless outside the training set. And the research community saw this, right? Which led to developing crucial tools like parameter priors and regularization techniques specifically designed to reduce the effect of overfitting.
Like adding a penalty for being too complex.
Exactly. Regularization, conceptually, is like saying, okay, find a good fit, but prefer simpler, smoother explanations. It discourages those wild, wiggly curves that just memorize noise. But these solutions had to be invented because the problem was so bad. It was this constant cycle of challenge, understanding, and innovation.
Okay, so overfitting was one massive hurdle. Another was just the sheer scale problem. And this showed up in a couple of ways.
Right.
First, early neural nets were often really shallow, few layers, maybe just one or two between input and output. Now, theoretically, there's this thing called the universal approximation theorem.
Yes. It says a single hidden layer network can approximate any function, given enough neurons.
A feed-forward network with a single layer is sufficient to represent any function.
Yeah.
Sounds great.
Right.
But there's a huge practical catch. To actually do that for complex functions, the layer may be infeasibly large and may fail to learn and generalize correctly.
Meaning you'd need a ridiculously massive number of neurons in that single layer.
Astronomically large. Computationally impossible to build, let alone train back then. So the big insight, which took a lot of time, theory, and crucially better computers to really explore, was that using deeper models can reduce the number of units required and can reduce the amount of generalization error.
Depth over width. Hierarchy.
Exactly. Instead of one monster layer, you use multiple smaller layers. The idea is they learn hierarchical features. Maybe the first layer finds simple edges, the next combines edges into shapes, the next recognizes objects from shapes.
Much more efficient computationally and in terms of learning.
Way more efficient and powerful. But even if you could build deeper networks, there was another scale problem. High-dimensional data sparsity.
The curse of dimensionality.
That's one. Real-world data often has tons of features, right?
Tons.
Hundreds, thousands maybe. Trying to plot points in a space with thousands of dimensions. It's just incredibly vast and empty.
Yeah, everything is far away from everything else.
Right. In these huge spaces, your nearest neighbors need not be close to the target point
Yeah.
and can result in large errors. Simple pattern recognition gets really hard because the data points are just too spread out, too sparse to find meaningful clusters or trends.
The concept of closeness almost breaks down.
It does, and the usual bias variance trade-off, balancing fitting the training data well versus being too sensitive to it, it does not work as favorably for nearest neighbor regression in high-dimensional features. It just becomes harder to generalize effectively when your data is spread so thin across so many dimensions.
What's compelling there is seeing how the lack of scale wasn't just about the network architecture size, was it? It was fundamentally tied to the data itself.
Yeah, they were linked.
If you don't have enough examples, and those examples are scattered across this vast high-dimensional space, the network just has nothing solid to learn from. It's like trying to learn a language by hearing only a few random words spoken miles apart.
Good analogy.
You're missing the context, the patterns, the sheer volume you need to actually understand anything. The data sparsity meant that even if a network could theoretically represent something complex, it didn't have dense enough information to learn it from those scattered inputs. The problem wasn't just network size, it was the thinness of the data fuel.
And it wasn't just about the amount of data or how many dimensions it had. The quality and the variability of that data were huge roadblocks, too. Early systems were often dealing with incomplete samples, which made learning unreliable.
Garbage in, garbage out, essentially. But worse, because they didn't have enough good data to compensate.
Right, and this leads to a core statistical problem. Sampling variance. When you're training, especially on big problems, you can't possibly show the network every single possible input, right?
Impractical. Impossible, usually.
So algorithms were forced to act on the basis of incomplete samples, just a subset of the real world. And this naturally introduces noise into the learning signal. The actual derivative, the direction the algorithm should go to minimize error, gets masked by a certain amount of random variation from the specific sample you happen to draw.
It's like trying to steer by looking at only a small, possibly unrepresentative patch of the ocean. Your readings are noisy.
Exactly. The learning becomes unstable, inefficient. It might veer off course based on the quirks of the current sample. And this really showed up, as we touched on, in that difference between infinite domain CSPs and finite domain CSPs.
The messy real world versus the neat toy problem.
Yeah. Real-world sensor data, continuous streams, missing values, errors. That's infinitely more complex than a tidy, finite set of inputs like in Sudoku. Early AI just wasn't robust enough to handle that kind of messiness.
This really makes you wonder, doesn't it? How much real signal can you possibly pull out from limited, noisy data like that?
Not much, presumably.
Early networks, without good regularization or just massive amounts of data to average things out, were super vulnerable to these data quality problems. Every mistake, every missing value, every outlier could just throw the whole learning process off track.
Because there wasn't enough good data to overwhelm the bad.
Precisely. And this forced researchers into those clean, tiny micro-worlds or toy problems.
Right.
Which, okay, they offered controlled settings for study, but they also reinforced that perception. These networks just can't handle messy reality. It was this vicious cycle, you know? Data limits, compute limits, algorithm limits, all feeding into each other, keeping neural nets stuck in the academic sandbox.
Okay, but despite all of that, the big critiques, the compute walls, the data struggles, some researchers just kept going.
The persistent few.
Yeah, they work quietly, often without much funding or fanfare, chipping away at the fundamental algorithms, the stuff that would much later unlock everything. You hear names like Yoshua Bengio mentioned often, someone who consistently points to backpropagation as a technique crucial to deep learning success.
Backprop, the workhorse algorithm.
Exactly. And a key development underlying it was the generalized delta rule. This was a big leap because it offered ways of constructing just the required set of representations. It directly tackled that Minsky-papered criticism about internal knowledge representation.
So it allowed the network to learn its own features, essentially.
Kind of, yeah. Instead of just relying on predefined input features, this rule let multi-layer networks develop a set of connections to and among the hidden units, which, in principle, allows the system to retrieve the correct input pattern from any unique subportion of the input pattern, provided there are enough hidden units.
Okay, so the hidden layers become capable of building more abstract representations from pieces of the input. That is crucial.
It was huge. It meant the network could learn to find and represent important features on its own, moving beyond simple input-output mapping. And backpropagation itself, That was the clever, efficient algorithm to actually apply these updates across many layers. It solved the credit assignment problem.
Which is basically, if the network makes a mistake, which of the potentially millions of connections is responsible and how much?
Precisely. Backprop gave an elegant way to calculate the gradient, the direction to adjust the weights for every single weight in the network, by efficiently passing the error signal backwards. This was the key to actually training deep models effectively, models with many layers which were needed to beat the limits of those early shallow networks.
Right. Without backprop, training deep nets would have been computationally infeasible.
Totally. And there were other algorithmic advances too during this quiet time, things like conjugate gradients, which were smarter optimization techniques, offering improved search directions compared to basic gradient descent, help find the minimum error faster.
Getting out of those local minima more easily.
Maybe. And researchers also developed ways to measure generalization and fight overfitting, like stacked generalization, feeding one model's output into another, and various complexity criteria like AIC and BIC.
Ways to balance model fit with model complexity, preferring simpler models that generalize better.
Exactly. Penalizing complexity, assuming simpler is often better for unseen data. These were all vital pieces of the puzzle, just patiently being put together over years.
And it's compelling, isn't it, that these weren't like sudden flashes of genius. They were slow, steady, incremental progress.
Yeah, hard graph.
Often in universities, where immediate commercial payoff wasn't the main goal. You think about Yann LeCun developing convolutional neural networks, CNNs.
Inspired by the brain's visual cortex, right?
Exactly. He looked at how the brain processes vision, hierarchically spots edges, then shapes, then objects, and built a computational architecture mirroring that. CNNs revolutionized image processing. That was another critical piece developed during those supposedly lean years. It shows how fundamental research, even cross-disciplinary inspiration from biology, could lead to huge breakthroughs, even when the field seemed quiet.
And that initial spark, the whole reason for neural networks in the first place, was that biological inspiration, right? The brain.
Absolutely, that was the guiding vision.
It was this powerful idea, maybe we can build machines that learn like brains do, that kept people going, even when the tech was lagging way behind the ambition. That vision was motivating. You see researchers like Demis Hassabis, later co-founder of DeepMind, recognizing early on the need for a deeper understanding of human cognitive processes to really push AI forward.
Right, looking beyond just the engineering.
Yeah. Even his early work, like creating game AI as a teenager, involved tackling complex problem solving and planning. You could see those as steps towards understanding and maybe replicating more general intelligence. And this bio-inspiration kept ideas alive, like distributed representations.
Even after Minsky and Papert questioned simple localized representations.
Right, the idea that distributed representations probably are used in virtually every part of the brain, where a concept is represented by a pattern across many neurons, not just one that remained appealing. Okay, maybe they can spread out the information, mix and obscure things, make it harder to interpret sometimes.
But the potential payoff was huge. Robustness, fault tolerance.
Exactly. If one neuron dies, the whole concept isn't lost because it's spread out. That potential for flexible, robust learning kept the idea alive.
This really makes you wonder, though, how much should AI copy biology? Where's the right balance?
It's a constant debate.
Yeah, and ironically, the Perceptrons book fueled that too. Some critics used it to argue that strong AI, truly conscious machines only makes sense given the dualistic assumption that where the mind is concerned, the brain doesn't matter.
The idea that intelligence is just computation, substrate independent.
Right. But as you said, the biological inspiration just wouldn't die. It kept feeding crucial developments like CNNs, which drew so directly from understanding the visual cortex. That tension between pure math computation and bio-inspired design, it's been incredibly productive for AI, hasn't it?
Yeah.
Pushing boundaries constantly.
Absolutely. So this whole period between the Minsky-Papert critique and the modern AI boom, often called the AI winter for connectionism. Less funding, lots of skepticism.
A tough time to be in that specific field.
For sure. But despite that chill, researchers kept at it. Quietly, persistently, laying groundwork that turned out to be absolutely essential later. A lot of this foundational stuff refining backprop, early CNNs happened in university labs, often on shoestring budgets. Yoshua Bengio has pointed out The importance of academic freedom and collaboration in effective research during this time.
Yeah, that freedom to explore without immediate commercial pressure.
It allowed for that deep theory, the careful algorithm development that was needed. Those lean years weren't wasted, far from it. They were critical for really understanding why networks failed, what the real limits were, and what exactly was needed. Data, hardware, better algorithms for them to finally break through.
It allowed for digging into optimization, generalization, the fundamentals of learning from data.
Without that patient groundwork, the later AI explosion just wouldn't have happened. It couldn't have.
It's truly a powerful story of scientific resilience, isn't it? Just imagine the determination needed to keep working on something that most of the scientific world has basically written off as a dead end.
Yeah, must have been tough.
But that period, that meticulous work on theory and algorithms, it was absolutely essential. It meant that when the conditions did finally change, when the data floodgates opened and the hardware caught up, the technology wasn't starting from zero, had this solid, well-understood core ready to go. That quiet persistence really paved the entire way.
Which brings us right to that tipping point, the moment things really changed, and maybe the single biggest shift that let neural networks finally leap from toy problems to real data was just the sheer explosion of data, digitized, accessible information everywhere.
Suddenly, that crippling lack of data scale wasn't the main problem anymore.
Right. The bottleneck shifted. This tsunami of data became the fuel neural nets had always needed. And it wasn't just data appearing passively, it was driven by this intense mass harvesting, a real collect-it-all mentality. Kate Crawford talks about how the creation of contemporary AI systems depends on exploiting data at scale.
Mining everything, public web, social media, digitized records.
Everything. Think of Google's early vision. Build a mirror of the real world, where anything that you see in the real world needs to be in our databases. That sheer volume directly tackled those old problems.
Overfitting, sampling variance.
Massively mitigated. With enough diverse examples, millions, billions of data points networks could finally learn robust general patterns. They could see the real signal through the noise instead of memorizing errors or getting lost in sparse, high-dimensional spaces.
The statistical power of huge data just overwhelmed the noise and the sparsity issues.
Exactly. The underlying meaningful patterns could finally emerge even from messy inputs. They became less brittle.
What's compelling there is how data went from being the problem, not enough of it, to being the solution, the fuel.
Totally.
Before, that problem of sampling variance meant small, incomplete data sets just hid the true patterns, right? Made learning unstable. But now, with hundreds of millions, billions of examples, those issues became manageable. It let those sophisticated algorithms developed in the lean years finally show what they could do.
Because they finally had enough information to learn from.
Precisely. Look at that epic AI for sepsis detection you mentioned, trained on information on over 250 million people. That scale is just... It's a different universe from the toy problems. It's real-world impact, saving lives, driven by big data. The data scale finally matched the algorithmic potential.
And right alongside big data came the other essential ingredient, the incredible exponential growth in computing power.
The muscle to process all that data.
Exactly. The raw horsepower to train these increasingly huge and complex networks. It was the perfect storm. Data, algorithms, and now the compute.
Ray Kurzweil calls it the law of accelerating returns, right? How information technologies like computing get exponentially cheaper because each advance makes it easier to design the next stage of their own evolution. Moore's law is just part of that bigger picture.
Yeah, this relentless exponential progress. It meant calculations that were once completely impossible, took too long, cost too much, just became routine, affordable even. But the real game changer, specifically for neural nets, was the GPU, right? The graphics processing unit.
Absolutely pivotal. Designed for video games, turns out they were perfect for AI.
Perfect. All those parallel calculations needed for rendering graphics. Turns out they map beautifully onto the matrix multiplications and parallel processing deep inside neural networks. That, plus advances in distributed computing linking many machines together, suddenly allowed training models with billions of parameters.
An unimaginable scale just years before.
Completely. And this ability to handle massive computation meant that deeper models, networks with many, many layers, could finally be trained effectively. We moved past the limits of those shallow networks Minsky and Papert had correctly pointed out, were infeasibly large if you tried to make them wide instead of deep. The hardware finally enabled the deep architectures.
It's compelling how often you hear that phrase now, right? It's all about the computer power, especially for things like deepfakes. Training a really good GAN, a generative adversarial network, to create convincing deepfakes. It needs large GAN networks trained on powerful computers, requires the most powerful computer with the most data. The theory, the algorithms like GANs, they existed or were developed based on that earlier work. But it took the hardware revolution, especially GPUs becoming AI workhorses, to make them practical realities. That's what turned neural nets from lab curiosities into tools changing everything. The engine was designed, but it needed the fuel data and the chassis hardware.
So with all those pieces finally in place, algorithms matured, data abundant, hardware powerful neural networks just burst out of the lab. They left the toy problems far behind, tackling incredibly complex, real-world challenges across almost every field imaginable, sometimes achieving things that feel, well, superhuman.
The transformation has been staggering, really.
Think about healthcare. That epic sepsis detector, using records from over 250 million people, finding sepsis signs hours before doctors often could, a plug-and-play tool that could literally decrease deaths due to sepsis without huge new investments.
That's a world away from early AI struggles with limited, noisy medical data. Just impossible back then.
Or look at creative stuff. Modern GANs, trained on a lot of data on powerful computers,
Ugh.
creating deepfakes so good they can deceive all ordinary deepfake detectors. Okay, raises huge ethical questions.
Huge question, yes.
But purely technically, it shows incredible capability in complex generation. Far cry from struggling with basic pattern recognition. Then education. You've got AI tutors like Conmigo. It can walk students through,
Right.
challenging questions, ask follow-ups, make suggestions, engage them with conversation, content quizzes, meeting them right at their learning edge.
Personalized learning at scale, adapting to individual needs, not just rigid rules.
Exactly. Moving beyond those old, brittle expert systems. And maybe the most stunning example, science itself. DeepMind's AlphaFold, a neural network that can accurately predict how the sequence of amino acids in a protein will determine its 3D structure.
The protein folding problem, a grand challenge in biology for decades.
Decades. Legions of top human scientists had inched painstakingly forwards on it. AlphaFold basically solved it in 2020, according to many, demonstrating truly superhuman AI capabilities, accelerating scientific discovery itself. It's mind-blowing.
It is, but it's also compelling to see how even with these incredible successes, new challenges emerge, right?
Always.
Judea Pearl, a giant in AI, critiques deep learning's data-centric approach. He argues it often leads to opaque models that cannot explain their reasoning, black boxes. They lack things like counterfactual reasoning, understanding what if.
So they're powerful pattern matchers, but maybe not truly understanding in the human sense.
That's the debate. So yes, we're way beyond toy problems in terms of what AI can do, but the quest for AI that's truly understandable, explainable, trustworthy, especially in high-stakes areas, that continues. The challenges just evolve. They get more sophisticated as the capabilities grow. Hashtag Tad.
Wow. What an incredible journey we've traced today, haven't we? Seeing neural networks go from being these academic toys, almost footnotes in AI history for a while, to being the absolute driving force behind technologies changing everything.
Really wasn't overnight success, was it? Decades of struggle.
Not at all. It was this long story of dedicated people wrestling with really fundamental questions. How do you handle massive, messy data? How do you break through computational ceilings? How do you even design architectures that can really learn, generalize, build useful internal representations?
All those hurdles we discussed.
Yeah. And that pessimism back then, the AI winter for connectionism, it wasn't the end. It was more like a necessary pause, wasn't it? A time for that deep theoretical work, the algorithmic refinement, that made sure when the stars finally aligned, when big data arrived, and powerful GPUs provided the needed horsepower, neural networks were ready. Not just ready to emerge, but ready to absolutely soar.
It's truly compelling how that history suggests a kind of pattern, maybe. Even now, with AI making these exponential leaps, we're still wrestling with new versions of those same old foundational problems.
Like what?
Well, as one source pointed out, researchers today still see possible problems with their underlying architecture and training that may, at some point, limit how capable they can become. Things like, are we going to run out of data to train on, especially high-quality data for the biggest models? Or will the cost and effort of scaling up the computing power just become too immense, practically or environmentally?
So the bottlenecks just shift again.
They might. And it makes you wonder, Are today's unsolvable AI challenges just waiting for the next big breakthrough in data availability, or maybe quantum computing or some new hardware, like the perceptron waited for backprop in GPUs? Or do they need something more fundamental? A true paradigm shift in how we even think about intelligence, maybe like the shift that brought neural nets back from their winter in the first place. The history suggests it could be a bit of both. Incremental progress punctuated by real shifts in thinking.
So maybe a final thought for everyone listening.
Yeah.
The next time you use some amazing AI, generative art, a life-saving medical
Yeah.
diagnosis, take a second. Think beyond the magic trick. Remember those decades of quiet, persistent effort that turned dismissed toy problems into these technological titans? And then maybe ask yourself, what seemingly impossible challenge today, what looks like a dead end right now, might just be waiting for its own perfect storm, the right data, the right hardware, or maybe that one brilliant overlooked algorithm to finally align and unlock a future we can barely imagine.
A provocative thought to end on.
Thanks for joining us on this deep dive.